Thank you. So, hi everybody, I'm Martin Baillon, and I'm going to present you a joint work with Pierre-Marie, Pédrot, and Assia Mahboubi called In Cantor Space, No One Can Hear You Stream, There Is No Alien Way to Compute. So as the title may suggest, this is a talk about continuity of Martin-Love type theory definable functionals, a formal proof of it in the ROC proof assistant. So the outline of the talk is going to be very simple. First, I'm going to talk about what does it mean to be an MLTT definable functional. Then I'm going to talk about continuity. Then I'm going to define all. And then I'm going to prove continuity of all MLTT definable functionals. So let's get going. What is an MLTT definable functional? So the outline of this part is going to be very simple. First, I'm going to define MLTT. So when I say MLTT, I mean Martin-Love type theory, so dependent type theory together with pi types, sigma types, booleans, natural numbers, equality, and the universe, which I write with this square, and it's called type 0. So that's what is going to be in my formalization in ROC. Now, when I say an MLTT definable functional, I mean a functional from the Cantor space to natural numbers. So I actually mean a closed term of Martin-Love type theory from NAT to bool to NAT. Okay. Now, if you look at such a closed term, you will see that there are two kind of properties you have. The first is that in MLTT, a term like this will not have any way to inspect its arguments. So any argument in the Cantor space is actually a black box for this functional. The only way for it to explore its argument is to ask queries. And now we have another property for MLTT, which is that it is normalizing. So if you apply f to any concrete alpha, it will reduce to a natural number in a finite number of steps, which is called canonicity. And so f will only ask finitely many queries to its argument alpha. Okay, so that means that if we were to draw out all possible executions of f applied to an argument alpha, we would have something like, first we ask question m, we have two possibilities, either alpha answers true or false. Then maybe we reach a value, maybe we ask another question, then maybe we reach another value, we ask another question, and at the end, we get some kind of tree like this. Okay. And this is what I'm going to call continuity. So to be a bit more formal, we are going to define a dialog operator, which might remind you of something you saw an hour ago in the invited talk. So given the type A, dialog of A is the type of well-founded Boolean branching trees with inner nodes labeled in natural numbers and lives in A. So basically, it's what you expect. So if you have A in A, the leaf A is of type dialog of A. You also have the leaf B, and you have this kind of trees where M, N, and K are natural numbers, and the values of the leaf are of type A. Okay, and now, given such a tree, we can actually make it dialog, which is why it's called dialog tree, if you have an element from the Cantor space. So we define a decode function, which takes a dialog tree and an element from the Cantor space, and it will use the tree to compute a value of type A. So it's by recursion on the dialog tree. If you're on a leaf, you return the value on the leaf. And if you're on a node, you use alpha to pick one of the two branches and keep going with your computation. So for instance, leaf A returns value A, leaf B returns value B, and then M, well, you ask alpha about M, let's say alpha is equal to true, we go to N, let's say alpha of N is equal to false, we go to K, let's say alpha of K is equal to true, then the value is C. Okay, and now a function f is going to be called dialog continuous if there exists a dialog tree that represents all the computations of f. Basically, every time you call f on alpha, then you can simply look at the dialog tree, do the computation I just described, and get the value that f of alpha is going to return. Okay, so now we have continuity, we have MLTT definable functionals, so we are almost there. What we need is to add all. So when I say that yes? I'm sorry, I don't. Yes, yes, that's actually what I'm going to say right now. So when I say I want to prove that all functions definable in Martin-Löf type theory are continuous, dialog continuous, I could mean three things. The first thing would be I want to make a model of MLTT together with some proof that any function is dialog continuous, which I write C underscore D. I could mean the continuity rule, which would be to have only at top level I'm able to construct the dialog tree. So if I have a closed term f, I can build through some kind of meta computation the dialog tree and put it back in the theory. Or I could mean something even weaker, which I call external continuity, which is to say I take a term of my theory and I go in the meta, I build the dialog tree, and now I have some kind of meta proof that the dialog tree actually computes what the term computes, but I cannot put anything back in the theory. Okay. In this talk, I'm going to present a proof of external continuity, even though we believe that we have a proof of the continuity rule, and someday we will have a proof of the continuity principle, but that's for you to work. So what is our battle plan? First, I'm going to define a well-chosen type theory. Then I'm going to prove normalization for this theory. Yes? I have a... Yes? The consistency, well, so I'm completely proof relevant. So if you wanted to add as an axiom, let's say in S prop or strict proposition, then it's consistent because we have semantical models like sheaf models, and so we can add it, and it's completely consistent. What I'm trying to have is to actually get the concrete dialog tree and play with it. Okay? So as I was saying, I'm going to define a well-chosen... Yes? I'm sorry, what Yes. Yes. Well, actually, you can do it by parametricity. If you have the external, then you get the rule. But I'm not trying to go into it right now. We can discuss it later if you want. So as I was saying, I'm going to define a well-chosen type theory. I'm going to prove normalization for this theory. And then I'm going to derive continuity from a modified canonicity theorem. So what is our theory? Our theory, which I will call split type theory, is going to make use of something you might have heard of, which is forcing. So I write it split type theory like this, and it will simply be Martin-Löf type theory together with a special generic sequence of type nat to bool. Might remind you of something. And now, if we have a derivation sequence in split TT, we don't have only one context, we have two contexts, gamma and what I call L, which is the list of the things we know about the generic sequence. So it's a list of couples of natural numbers and booleans that represent the finite information we have about the generic sequence. Now, what that means is that if we apply our oracle to a natural number, and if we have the value in the list, then it will be definitionally equal to true or to false, depending on the value of the list. And that is exactly what I'm trying to say there. You're like 1 second earlier. So yes, here n is a meta natural number, and this n with a bar is the injection of a meta natural number inside the theory as a term of the theory, like a stack of successors on top of 0.
And L terms of number.
Yes. So now, how do I gain knowledge about my generic sequence? I have a sheaf rule. So basically, imagine you want to prove that T and U are convertible, but they mention the generic sequence, and maybe you don't have already all the information you need. Well, if you have a question which is not already in the domain of the list of values, then you can keep the computation going on the left with the value true and on the right with the value false, and then derive more equations and compare the two terms. So for instance, let's say you want to prove that if the gamma of 5 then 0 L0 is convertible to 0 under the empty list of knowledge, so you don't know nothing about the generic sequence, and especially you don't know the value about 5, then you add true on the left, then you compute, it reduces to 0, convertible to 0, so that's okay. And now the same thing on the right with false, and you get 0 convertible to 0, so this is convertible to 0. Now, what about continuity with everything I just said? So the idea is that we're going to get continuity from a canonicity theorem about our theory. So the usual canonicity theorem you would have for Martin-Löf type theory would say that in the empty context, you have a term T of type nat, and it will reduce to some concrete natural number in a finite number of steps. Now, in split TT, this is not true, because even in the empty context, you might mention the oracle, the generic sequence, and so you will not reduce to a concrete natural number, where you will be stuck on the information you don't have. So what we have is a modified canonicity theorem, which says that you will have a tree of splits, and on the leaves of that tree, you will reduce to a concrete natural number, different one every time. So for instance, we have this term of split TT. If the gamma of 5, then 0 else 1, we will split on 5, and on the left, it will reduce to 0. Sorry, and on the right, it will reduce to 1. And now, if you look at it, you get a dialog tree, which will exactly be the dialog tree we want to prove continuity of the closed term we have. Okay, so to get continuity, we want canonicity, and to get canonicity, we are going to prove normalization of the theory. So I'm going to normalize split TT, so I'm not going to do it right now, because I have like 5 minutes left. But I'm just going to highlight a few interesting points of the proof. So usually, when you want to normalize some theory, you're going to provide a semantical meaning to what it means for a term T under some context gamma to be in A. And it will involve reducing to something. That's what we're doing. And here, we are going to have a distinction between what I call strong reducibility, which will be reducibility right now for the world at hand with the information we have right now about the generic sequence, and weak reducibility, which would be some kind of model reducibility, like reducibility up to a tree of splits. Exactly like canonicity, you have canonicity right now, I reduce to a natural number, or I do some splits and then I will reduce. So just to explain strong reducibility, well, first, it's obvious, but the reduction we're considering is just the usual reduction plus a rule that says that if the information is in the list, then you reduce, okay? And now we're going to have 4 predicates, what it means for a type to be reducible, for a term to be reducible at a type, and the same for the computation rules. And so, for instance, if we are trying to define what it means for term T to be reducible at the Boolean type under some context gamma and some list L, well, it means that either T will reduce to true, or T will reduce to false, or T will reduce to some neutral well-typed term. So neutral means that it is blocked on a variable. Not the generic sequence, an actual variable. So now a case that I'm not considering here is that if T reduces to the generic sequence applied to something. And this is exactly where we need to do some kind of split to keep the computation going. And this is weak reducibility. So, which I write like this. And basically, like with an image, it looks like this. It means that we do a bunch of questions, and on the leaves of the tree, we are going to have strong reducibility every time. So it's really the same thing as canonicity, where either you reduce right now or you reduce later. You can think of it with this kind of modality. And now we have a new inductive type, which is a tree of split starting from the knowledge we have right now. So we have some knowledge, like the value at 5, and then we can ask a bunch of questions, and we have different leaves which make all the possible answers for the generic sequence. And now the weak reducibility will be there exists this new dialog tree there, starting from the world at hand. And for any further world that answers all the questions of the dialog tree, then you will strongly reduce. Okay? Now, we need to prove it, and we prove it in ROC, building on some previous world work by Arthur Adjech and Meven and many other people called Martin Leuf-Alacoque. We finished proving it some weeks ago. So splitity is normalizing. Everything is great. We live in the best world there is. So thank you, everyone.